Hello everyone and welcome to the 13th lecture of Digital Image Processing of Remote Sensing Data course. And in this particular discussion, we are going to discuss frequency domain Fourier transformation. In the previous lecture, we have discussed about the spatial domain, how using a spatial domain concept, we can design different kinds of spatial filters, convolution filters, and can improve our images as per our requirements. So similar things can also be done, but instead of exploiting a spatial domain, we can exploit the frequency domain through Fourier transformation, and we can also achieve quite good results. So this discussion we are going to focus on this. We know that a wave which is shown here can be segmented into different waves. So this wave, the lower one, is the sum of all these waves, and this is what basically it was in 1768 by Jean-Baptiste Fourier. He mentioned that any periodic function can be expressed as a weighted sum, and this is what the weighted sum of sines and or cosines, and that we call as Fourier series. So this the fundamental was laid down in 1768, and at this function at the bottom, which I have just mentioned, is basically is the sum of four functions above, which you can see here, of different wavelength. So Fourier's idea in 1807 that periodic functions could be represented as a weighted sum of sines and cosines was met with skepticism. People didn't appreciate at that time, but later on, now in digital image processing, it has been adopted. Though we are here, we are mainly thinking in a linear fashion, but also for a remote sensing data, which is a two-dimensional data, still we can employ this thing, which we will see very soon. So the same example is given here, that this is the combined sum of all these wavelengths, waves which are shown here. So the variations in digital numbers along a line on this image A can be expressed as a range of sine waves, which is shown here in the lower figure, of different amplitude and frequencies. So the different amplitude and frequencies, when you sum, you get this thing. So the cumulative effect is the same as the real spatial frequency distribution of the image. Now other functions can also be expressed an integral sines or cosines multiplied by a weighing function, that is Fourier transforms, and function can be recovered by inverse operations with no loss of information. This means basically that what we do through from a spatial domain, we transform into frequency domain, do the filtering there, and once the filtering is done, we reverse the transformation or inverse transformation, Fourier transformation, and we restore the image with better results or or filtered image. So this is a two steps process. First is or rather three steps process. First is that is from a spatial transformation from a spatial domain to frequency domain, do the filtering within the frequency domain, and then come back into the spatial domain. And of course the main aim which of entire this course is to enhance the quality of images so that we can do the better interpretations. So any image or natural scene can be regarded as and reconstructed from a spectrum of sine waves with different directions, wavelength and amplitude. Few examples we have seen, and such a reconstruction is known as Fourier synthesis and the dissembling of an image into family of sine waves in a Fourier analysis. Because the filtering, once you transform from a spatial to frequency domain, then filtering becomes much easier, and you can select where things have to be filtered out, and later on you transfer back or inverse transformation. So spots, lines and bars that forms the targets for the test of acuity and form images too are themselves made up of sine waves, and small dots and closely spaced lines are dominated by high amplitude at high frequency, and this is why they are difficult to recognize. so as size increases of these dots, high frequency components become lower in amplitude, and those in frequency range to which the eye is attenuated increase, and perception and distinction become easier of these digital images. And beyond this, however, very low frequency components increase in amplitude, effectively degraded perception and distinctions. So mathematically, the technique for separating an image into various frequency component is basically the Fourier analysis, and the basic principle is illustrated in this figure, as also we have seen this figure, that we are this cumulative image, which is a sum of all these images, so that we can take out different frequency components, and later on, once we remove that, suppose noise is coming from only one frequency or one amplitude, a particular frequency wave. So we can remove that one, and then we recombine and get a new results, filtered results. So the Fourier transformation of an image is a two-dimensional, so things have to be little different. The result of such a separation expresses the spatial attributes of an image in terms of their frequencies, amplitude, and their orientation, and it is a transformation that enables certain groups of frequencies and direction to be emphasized, same as in the ultimate aim is to filter the image, make certain enhancement in the image. So same as in spatial filtering technique, we try to emphasize some features, maybe regional features or local features, and we want to de-emphasize certain. So similar things we will do, but different way. Instead of spatial domain, we will work in frequency domain. So though that emphasize high frequencies and suppresses low frequencies are high pass filters. Similarly, in spatial domain also you have seen high pass filters and low pass filters. Similarly, there are medium and low pass filters in frequency domain too. Moreover, selected image ranges of spatial frequencies can be removed or retained in the resulting image using band stop and band pass filter. Basically, the concept of this filtering techniques have come from electronics, where like in audio or video some noise is coming, you want to remove, so you identify that frequency and then remove that frequency wave from the total signals. So the process is analogous to electronic filtering, as I have just mentioned, in amplifiers to reduce hiss and rumble, enhance the bass or treble, and so on in a sound recording. And filtering can be implemented through the Fourier transform when it is said to operate in frequency domain or in a spatial domain of image itself by process as convolution. Convolution filtering we have already discussed, and in frequency domain filtering is more powerful, because here you know that which are the features are causing noise in your scene, which are the features which are causing distortions in the scene. So the identification of those things is much easier in frequency domain than in spatial domain. That is why it is more powerful compared to spatial domain. But processing is more required, better understanding of images and further processes is required. Therefore, people generally prefer a spatial domain filtering rather than frequency domain, but it is more powerful, the frequency one. So instead of using a spatial domain, that is the x and y coordinate space of an image, an alternate coordinate system that can be used for image analysis, that is the frequency domain. And in this approach, an image, as mentioned earlier also, is separated into various spatial frequency components through application of mathematical operation that is known as Fourier transform. And conceptually, this operation amounts to fitting a continuous function through the discrete digital number values if they are plotted along each row and column in the image, and the peaks and valleys along any given row or column can be described mathematically by a combination of sine and cosine waves with various amplitudes, frequencies, and phases. And the frequency domain field refers to the plane of two-dimensional discrete Fourier transform of an image. And the purpose of the Fourier transform is to represent a signal as a linear combination of sinusoidal signals of various frequencies. So this is how mathematically that there are different options are available, like one dimensional Fourier transforms and its inverse equation, both are given here. Similarly, two dimensional Fourier transform and its inverse, here it is also continuous case, it is also continuous case. We will later will see discrete case. So this is one dimensional Fourier transform, this is two dimensional Fourier transform, equations are given. Here this is one dimensional Fourier transform, but discrete case, not continuous case, and both equations, Fourier transform equation and inverse equation. So there are various options are available here depending on requirement of your filtering for the image. So after an image is separated into a component spatial frequencies, it is possible to display these values in a two-dimensional scatter plot known as a Fourier spectrum. And this Fourier spectrum basically will allow us to design a filter and then remove the noise or whatever features which you want to de-emphasize. So lower frequencies in seen are plotted at the center of a spectrum. This is important to remember, that the lower frequencies in the scene are plotted at the center of a spectrum, and progressively higher frequencies are plotted outward, in which this is in a two-dimensional scatter plot or in a Fourier spectrum. And this features trending horizontally in the original image result in vertical components. Is a rotation of the components here or axis here, that the originally when they are trending in horizontal, they will appear in this Fourier spectrum along the vertical component, and features vice versa is also true, that features aligned vertically in original image result in horizontal components in the Fourier spectrum. So there is a rotation by 90 degree. This one has to remember while interpreting the Fourier spectrum. So if the Fourier spectrum of an image is known, it is possible to regenerate the original image through the application of an inverse Fourier transform. So for one dimensional Fourier transforms, both inverse and forward, we have all seen for two dimensional, continuous and discrete. And this operation is simply the mathematical reversal of Fourier transform. Hence the Fourier spectrum of an image can be used to assist in a number of image processing operations. An example like spatial filtering can be accomplished by applying a filter directly on the Fourier spectrum and then performing a inverse transform. Inverse transform has to be performed, that is the last step in Fourier. Now example, this is an image, and this is the Fourier spectrum. And as mentioned that the components or features which are horizontal here or along, in more or less along the xy, they will appear here, and the features which are in vertical directions, they are appearing here. And as also mentioned earlier, that the low frequency features, as mentioned here, that the low frequencies in scene are plotted at the center of a spectrum. So the low frequency are plotted at the center here, and high frequencies are at the periphery or outside, away from the center. So this is how the Fourier spectrum is interpreted. Now filtering, if we want to filter, now we know which direction, so it becomes very easy now. So if we want to filter, say the features which are roughly say north-south, north-south, south-southeast direction, then we will remove these from the Fourier spectrum. And once we go for inverse transformation, then these features, directional features will be de-emphasized. So the features which are here, if I remove from here in the Fourier spectrum, then the resultant image will not show them, or they will be de-emphasized. The examples are here given again, that this is the original image, this is the Fourier spectrum. After filtering and then inverse transformation, this is the result. So the high frequency, low frequency features which are in the center has been removed, and only high frequency features here have been kept which are away from the center, and therefore in the resultant image you are seeing this kind of where high frequency feature. So spatial filtering in a frequency domain, which is the A, high frequency blocking filter, which is given here and B, inverse transform image, and low frequency blocking filter and inverse transformation there. So this frequency filtering operation is carried out as per the following steps. The original image is transformed to its frequency domain representation using Fourier transform. Then image processing, selecting an appropriate filter, transform functions and multiplying it to the elements of Fourier spectrum. The inverse spectrum, inverse Fourier transform is performed to return to the spatial domain for display purposes. So you restore the image after filtering, and this is what the in short this is what the inverse Fourier transform. Few more examples are given, like here this is the image. This is the Fourier spectrum. You want to remove certain frequencies, you want to emphasize certain frequencies, you can do it as in this example is done. And then this high frequency features have been removed from the perimeter side, and then only low frequency features. So regional features have been emphasized, whereas high frequency features have been, or local speckle kind of thing have been removed, and the high frequency features have been de-emphasized, and you see a very smooth image. So this image for interpretation is not that good because it is suffering from lot of distortion, lot of errors, like these almost missing lines or horizontal lines are there. They will appear here in Fourier transform as vertical lines. So if I remove this, then I am removing basically these lines. And similarly, if I remove the outside in this Fourier scatter plot away from the center, then I have removed the high frequency features, and this is what you see here. So on a different, this is the example of JER 5251 short wave infrared image, and on which is the band 8 covering the Etrurian highlands. So this is one example of how beautifully an image with Fourier transformation and filtering can be improved for imaging. Another example from Landsat MSS, that in Ethiopian highlands, this is which is severely affected by spurious low data, and this and the Fourier transform, if you spectrum, if you look, you would find vertical lines kind of thing. You can remove during filtering process, go for inverse Fourier transform, and this is what you see. So all lines have been removed. Here you get very good results. Whereas in case of spatial filtering, what we do, we take out the average of adjacent pixels which are not missing, and then we take an average and substitute value for missing pixels. That is basically sort of cosmetic and not a pure scientific method in that way. And if there are many lines are missing, then spatial techniques will not work. But here in Fourier transformation, it is very easy to remove such distortions or noises which are present in the data. And this is a very common feature of remote sensing data. Many times, because of some malfunctioning of sensors or CCDs, some transmission problems, you may get certain lines which need to be removed in order to restore the original quality of an image, so that maybe that image of particular day or particular area may be very important, and therefore the technique is available. The best suitable technique for here is the Fourier transformation. So this methods involves an identifying frequency. It's just a recap of the thing, identifying the frequency and amplitude of stripping and other pervasive systematic effects. Systematic and distortion defects can be removed very easily, superimposed on the real variation by analyzing a Fourier transform of the image, and the periodic noise can then be identified as a signal and suppressed by filtering in frequency domain. Again you go back for inverse transform to spatial domain, then restores a cleaned up image. And in frequency domain, the noise is isolated as distinct signals and almost wholly removed by specifically designed filters that operate the frequency domain. Few more, like one example here, horizontal lines are there in, as mentioned earlier, that in Fourier spectrum they will appear very strongly in form of vertical lines. So once these vertical lines are removed, inverse transformation is performed. This is what you see. So it is very hard to interpret this image, and if you make interpretations, you may make some wrong interpretation, wrong decisions about the features which are present. But if you filter it through Fourier transformation function, then you may restore a very good quality. So this is A is airborne multispectral scanner image containing substantial noise, as you can see. B is the Fourier spectrum of the image, that the noise pattern which occurs in a horizontal direction in the image will appear vertical will appear as a vertical direction in the Fourier spectrum. Now the C is, as I have mentioned, that the vertical wedge block filters that has been applied to this block filter has been applied, and this filter passes the lower frequency components of the image but blocks the high frequency, because these lines are appearing as high frequency components of the original image, and this is inverse transform of C. So the image restoration is the very good quality of this analysis. So Fourier analysis is useful in a host of image processing operations in addition to spatial filtering and image restoration applications. However, most image processing is currently implemented in the spatial domain. Also earlier I mentioned that many people prefer, and because they find easier to understand the spatial domain. But if they adopt and go for a Fourier transformation functions and remove the noises, high frequency features and other thing, then it is equally good or much better. More powerful technique is definitely Fourier transform, because though it involves number of complexity of computation required in frequency domain. Many digital image processing softwares which are not having advanced features may not have even frequency domain filtering techniques or this Fourier transformation functions. This situation is likely to change as we improve in the computer hardware and software, and more research may be required to make these things easier. So this brings to the end of this filtering techniques. In previous lecture we have discussed spatial filtering, and in this one we have discussed the frequency filtering techniques. Both are very useful, very powerful, but frequency domain filtering for certain missing line, higher frequency features, it is much more powerful, but it requires more computation time and better understanding, and maybe all digital image processing softwares may not support, whereas very standard normal low-end digital image processing softwares will definitely support spatial domain filtering techniques. So if one is having both in their systems, then both should be tried on image and see that and do the comparison and see that which one is getting better results. I am sure you would get definitely better results when you will apply for Fourier transformation functions. So thank you very much.